Okay, this is our video for simple logistic regression. So first off, we're going to set up by loading some packages. You're going to want dplyr, rocker, ggplot2, and caret. And we're also going to set the seed to 1 so that the results will be the same for me and you, but it still keeps things random. So first off, here's what the data looks like. We're using the iris dataset, which is built into R. It has 4 different variables that are all continuous. So sepal length is the length of a sepal on a plant, and it's measured in centimeters, and just like the width and the petal length and the petal width are all measured in centimeters. And then there are 3 levels of species that are built into the dataset: setosa, versicolor, and virginica. But logistic regression is meant for only 2 levels, so we're going to actually drop one of them in a little bit. So first off, we drop a level, so we're dropping setosa here, and then we're going to make it so that virginica and versicolor are 1 and 0 respectively. Here's a plot to show that this is the type of data that we would want to use logistic regression on, as there are only 2 different levels, so 0 and 1, and then we have the petal length plotted just to show that how it continues. You can see around 5 the species are either 0 or 1, so that's probably where our logistic model is going to have. So now we're going to get into making our model. First, we want to do this by creating a training data set. And by that, it's just a sample of our original data set, but it's half. So we're going to have 50 observations as our training data set. So now to make the model, it's very simple. It's just like in linear regression. You do species, then you put the little twiddle, and then you put the variable you want. In this case, we're only doing 1 variable to make things simple. Then, since it's logistic regression, you want to put that the family's binomial, so that just means that there's 2 different levels. And then you want to put your subset, which is the training data set that we made earlier. And then we can look at the summary of our model. So, just like in linear regression again, it's going to be pretty similar. We can look at petal length here and see that what the estimate is, and we can see it's significant. It's because it's less than 0.05, which is good. So that means that we chose a variable that's going to be accurate for this model. We can see how the model is making predictions by looking at the S-curve. So to generate an S-curve, we need to create all the x values into a vector. So all possible x values between 3 and 7. We just have an increment here that's small. And then we want to make predictions for these y value or for these x values, which is just done by using the predict function, creating responses. Then we want to make a data frame, which just puts the x's and the y's together. And then we want to make a plot. So we have the x on the x-axis, y on the y-axis, obviously. And we can see that from 3 to 4 of petal length, we're pretty close to 0 for these probabilities. And from around slightly after 5 to 7, you're pretty close to 1, which looks good. And then around 5, we're getting some pretty varied probabilities for petal length. So we know that around 5, things are definitely going to be less accurate when we're making predictions, which is fine. We just have to eventually make a cutoff point, which I'll talk about soon. So now we're going to make predictions for our real data. So earlier on, we made that training data set and we built our model based on the training data set. This time, we're going to make predictions for what's called the test data set. So it's everything without the training data. So you do this by using the predict function. We put our model there, and then we have iris2 with everything except for our training data set. And our type is response, because we're getting responses. So this type of model gives between a 0 or a 1 as its output. And what we need to do is find a cutoff point for what's going to be a 0 or 1. Because we want everything to be a 0 or 1, but it's not going to be that way in real life. You're going to have values like 0.5, 0.6, and you have to kind of decide what goes into what group. So we do this by looking at the precision recall F measure, which when it starts to slope off is when the sensitivity and the specificity are maximized. So on this, we have around 0.65 ish is going to be the cutoff point. And now you could change this later. This is just to tell you, like, it's around here, so we can definitely mix it up in a bit. So now we're going to put our predictions into one data frame here. So I just put in the petal lengths, I put in the predictions, I put in the truths, which is the actual values of what these are. And I labeled it as versicolor and virginica instead of 0 and 1, just to get a better visualization of what this is. So here's where we can plot the two plants, and we can plot the predictions, and we can plot the cutoff point to see how well our model is predicting everything. So on the left side, you want everything to be below the cutoff point, and on the right side, you want everything to be above the cutoff point. So for versicolor, it seems like our model is better at predicting since everything is below the cutoff point, which is the 0.65. And on the right side for virginica, our model is worse at predicting. We have about 3 that are going to be predicted inaccurately, which is fine. So if we move the cutoff point down, we could move it to like 0.5, and then you would have it more accurate for virginica, but then 2 of versicolors would be wrong. So I'm just going to keep it at 0.65 because it's very close to being 100% accurate, and it'll do fine. So now we can look at other measures of our model. So what I'm doing here is making our predicted class variable, which just means that if our probability is less than 0.65, we're going to make it a 0. If it's greater than 0.65, it's going to be a 1. And then I am changing that into the actual levels. Instead of 0s and 1s, we're making it versicolor and virginica. And then we're making what's called a confusion matrix, with the positive being versicolor. So the confusion matrix just gives us a bunch of measures. Here we're only going to be looking at a couple of them. So the sensitivity is the true positive rate. So if we scroll back up here, we can see that we did have a 100% true positive rate for versicolor because all of them are below the line, which matches up here. So our sensitivity is 1, and our specificity is 0.89, which also matches up with the above graph, which is pretty good. And our overall accuracy is 0.94. So this model worked pretty well. This data is meant to be pretty correlated, so that was quite expected.